Hello everyone, welcome to our video today where we're talking about biochemistry, chapter 4, carbohydrates. So the later chapters of biochemistry cover a more in-depth breakdown of carbohydrates, but right now these are just the basics and the foundation of this so that we can, take it a step further in later chapters. So let's get started. We have monosaccharides, which is a single carbohydrate unit. Okay, for example, glucose, or fructose, or galactose. Those are all monosaccharides. Okay, so then we have these monosaccharides can undergo esterification, which we'll talk about in a moment, oxidation reduction, or glycosidic formation. And glycosidic formation is really the glycosidic linkage that links carbohydrate monomers at their anomeric carbons. Okay, so we have disaccharides, which is two molecules, so two monomers together. And then we have polysaccharides, which is just a chain of those carbohydrate monomers, okay? So we have ketosis, which is when a ketone is the most oxidized. And then we have an aldose, which is when an aldehyde is the most oxidized in that carbohydrate, okay? Then we have glycogen, cellulose, and starch are all subcategories of carbohydrates, and they're really important. So we have glycogen, which has more alpha 1 to 6 glycosidic bonds than starch does. And I'm hoping you can see this. If it's not too clear, let's just see here. Hopefully you can see that. So glycogen is the energy storage for animals. And the alpha 1 to 6, these numbers represent which carbons in this cyclic carbohydrate are actually part of the bond connecting one another. So it's linking the first carbon to the 6th carbon, okay, to create this chain. So that's what these numbers mean. So again, the glycogen is energy storage for animals, and it just has more alpha 1,6 glycosidic bonds than starch does. So I believe it's approximately every 10 carbohydrates on this, every 10 monomers, every 10 monomers approximately, there is going to be a 1 to 6 glycosidic bond and just growing this chain, okay? Then we have cellulose, which is in plant walls and fiber, for example. So that's cellulose. And then we have starches, and starch is the energy storage for plants. So two different types of starches. So there's amylose, which is unbranched. So this means it's just a linear chain. And this is composed of alpha 1 to 4 glycosidic bonds. So just the carbon 1 to carbon 4. So that's just how that chain is created. And then we have amylopectin, which is branched. And it starts off with that linear amylose chain, but at every 25th, approximately at every 25th monomer in that chain, it begins to branch with a alpha 1 to 6 glycosidic bond. So that's the same bond that we saw in glycogen, but this is at every 25th approximately, and this for glycogen, it is at approximately every 10. Every 10, when I say every 10, I mean every 10, again, monomers as you go down this chain, okay? So those are just some important things to note as we get into later chapters as well about like what enzymes we have versus what enzymes we need to break down these bonds and things like that. We'll definitely go into later. So just understanding these basics is super important. So next we have the configuration a little bit in the stereochemistry of the carbohydrates. So deconfiguration is when the OH group is on the right of the highest chiral carbon, okay? And the L configuration is when the OH group is on the left of the highest chiral carbon. And for me, it took me a very long time to understand all these configurations because we have, different configurations in organic chemistry than we do for carbohydrates. So this this D and L configuration It's really for carbohydrates specifically, okay? And so, yes, enantiomers of a certain molecule will actually be the D and the L versions, okay? So if you had one that's D configuration and one that's L configuration of the same molecule, those would actually be enantiomers, okay? And we definitely did an organic chemistry video about enantiomers. And then we have diastereomers, again, a term we might be familiar with from past videos. And we either have epimers, which, the diastereomers can be broken up further into epimers, which are different at only one carbon. And then we have anomers, which differ at the anomeric carbon specifically. And the anomeric carbon is the new carbon at the ring closure. Okay, so you would have, let's say, a linear molecule. When you have this ring closure, for example, glucose, okay, when you look at it, it's a ring closure. The anomeric carbon is that new carbon that's created when the two ends of the chain come together. So that's just, again, some vocab. Definitely important to know the anomeric carbon, as well as these configurations. So next, we're going to talk about up here. Hopefully you can see, yes. Okay, so we have esterification, which is a sugar's hydroxyl group with a carboxylic acid to create an ester, okay? And then we have phosphorylation, which is a phosphate ester that is formed by transferring a phosphate group from ATP onto a sugar. So these are just two important terms, just to get the gist of what's happening. We do look at these reactions more specifically in other videos, but, for the purpose of this chapter, just knowing what these two things are is important. So now if we draw your attention down here, these are just, again, some just quick tips you should know. So we have maltose, which is a glucose plus a glucose. So again, this is a monomer, this is a monomer. This means this is a disaccharide. So this is a monosaccharide, disaccharide. So we have lactose equals galactose plus glucose, and then we have sucrose is actually glucose plus fructose, okay? So just, again, some things you should know. So if we're going to go back to the configurations that we were looking at before, this photo right here is this diagram is D-glucose, and I'm going to bring it down here so you can see a little better. Oops. Okay, so that there is D-glucose, and I'll explain why. So we have, here we go. All right, so this is D-glucose, right? Because we said D configuration, the OH is on the right of the highest chiral carbon. So in this case, the highest chiral carbon is right here, okay? And the OH is on the right. It could be here or here, but it's on this right-hand side of this highest chiral carbon. And it's the highest chiral carbon, it is connected, if you just look at what it's connected to. So this is the highest chiral carbon here, and the OH is on the right. If the OH was on this side, you would have L configuration, okay? We have alpha anomers, which is when the OH on the anomeric carbon is trans to the free CH2OH. And these two things took me a while to wrap my head around. And then we have beta anomers, which is when the OH on the anomeric carbon is cis to the free CH2OH. So when we say trans or cis, we've looked at this in organic chemistry, and when you have a double bond, cis would be on the same side, and trans is when they would be on opposite sides. So this is saying the OH on the anomeric carbon is on the opposite side of the free CH2OH. And for beta anomers, the OH on the anomeric carbon would be on the same side as the free CH2OH. Okay? So again, there's just some important definitions to note in this chapter that will be helpful later. So thank you for tuning in. As always, put your questions below, and we'll see you in the next video.